catch up with a few things which I cannot. The coffee break is long, so you can. Okay, very good, very good. So my name is Anton Lechner. I'm from CERN. I'm working since about 20 years on radiation transport problems for different machines. So I'm working on the machine side, not on the detector side. So I'm working on, in particular, on LHC operation, but also high luminosity LHC and also future colliders, muon collider, FCC, and we are also contributing to other machines. So in this lecture, I will give an introduction to machine detector interfaces for multi-TV muon colliders. I'm not so much speaking about lower energy muon colliders. As you know, in the past, there were also studies for Higgs factors at lower energies, but really the focus here is on multi-TV muon colliders. Okay, so the lecture is split into two parts. So in the first part, so this morning I will give a little bit of introduction. Then I will speak about the interaction region design, in particular about the final focus design and also the associated challenges. And then I will really focus on the sources of beam-induced background and the mitigation measures. So I will mostly speak about muon decay, but also a bit about incoherent electron-proton pair production, which is a beam-beam process, and then also about beam halo losses on the aperture, which can also contribute to the background. Then in the second part of the lecture, which is actually not tomorrow, but this afternoon, it has been rescheduled. This is given by Daniele. So we'll speak about numerical methods and tools for simulating the beam-induced background. So it's mostly about Monte Carlo radiation transport simulations. And he will also show some more results for the 10-TV collider. So we'll not show so many numerical results in terms of background spectra and so on, because this comes in the second part of the lecture. It's really about now introducing you to concepts and to get a bigger picture of the MDI. So first of all, what are let's start with a basic question. So what are the primary goals of the interaction region and the MDI design? Clearly, the first goal is to achieve the desired luminosity. This means to achieve the desired collision rate in the interaction point. And for this, we need a strong final focus quadrupoles, which you can see here in blue on each side, which squeeze the beam in the interaction point here to achieve the desired beta star. So I will also explain a bit more about beta star later on. So you already heard about beta yesterday, but it's good to repeat it maybe from different perspectives. So in order to be efficient now, these detectors need to be close to the interaction point. But on the other hand, we also need a sufficient long drift space to accommodate the detectors. You can see in the detector solenoid. So drift space meaning a space without any magnets. So this is important to have enough space here. Because we need, to accommodate really the full detector and the solenoid. This means that the magnets can also not be too close to the interaction point. So on the one hand, from the machine side, we want to have them close. From the detector side, we want to have them further away. Another important point is that we have to sufficiently provide a sufficiently large detector acceptance, as we already heard in the talk of Kevin before. But this means essentially we have to reduce the material budget in this drift, but in particular also in the central region here. But then we have to sufficiently mitigate the beam-induced background and also the cumulative radiation damage in the detector. And for this, we need shielding configurations. So you can see here, for example, this conical shielding absorbers here, which penetrates deep into the detector, and they partially perturb the detector acceptance. But this is still necessary to reduce the background. So as you can see, these are really partially conflicting requirements, and the MDI design is really about finding compromises here. So you might have seen the science cover last year, so illustrating this very important topic of the beam-induced background. So this is an artistic rendering of a decay-induced background based on Monte Carlo simulation. So it's just to say also that this is really an important point for the MDI design. So I have to switch on here, of course. So just a few words about the history. So proposals for multi-TV muon colliders already existed since decades. There was, for example, this feasibility study in the US in the 1990s. A bit later on, there was the Muon Accelerator Program MAP in the US, as also Daniel mentioned already yesterday. And now there's the International Muon Collider Collaboration. So interaction regions and the MDI studies for multi-TV machines already started more than 30 years ago. For example, here you can see Monte Carlo simulations of secondary muon tracks. These are beta height muons, which are produced, in fact, by photons produced in the electromagnetic showers of muon decay. Just to give you one example here. And they already performed first absorber design studies. But then in the scope of MAP, there were detailed MDI studies by Nikolai Mokov and others from Fermilab for a 1.5 TeV center of mass muon collider. So they were using the mass Monte Carlo code. So this is a Monte Carlo code developed at Fermilab. And you can see that some of the models they were using. So for example, this is the detector. This is some shielding configuration. You can see here the machine. And this here is the central region, just to have a focus on this to see what they were using. But at the same time, there were already very significant studies for the interaction region lattices for different, for example, different center of mass energies. Now in the IMCC, we're performing detailed studies, MDI studies for 10 TeV center of mass machine. So with a possible 3 TeV first stage, and we're using the Fluker Monte Carlo code. I just have to say we're also profiting still a lot from the concepts developed by MAP. So this is really, sorry, let me just adjust the microphone here. By MAP, because they were really introducing concepts which were already, I mean, really useful also for the 10 TeV machine here. Something more I want to say about this here. So in this lecture, we'll mostly focus about the 10 TeV machine. It's simply because it's a bit more challenging than the other machines, because at lower energies, of course, we cope with the same let's say, beam-induced background, but now everything is pushed much more, also in terms of machine design. I also have to change here, sorry, I forgot the change of the on the laptop directly. I also want to say that these MDI studies are still also very conceptual. So we don't have yet a technical design or a detailed integration study. So it's still something which has to be developed in the next years. We need engineering studies. We need to take into account that all the systems have to be well integrated together. So for the moment, it's really just conceptual, really with a main focus how we can cope with the beam-induced background. Okay, let's start a bit with the muon collider parameters here. So these are the IMCC parameters. Daniele already introduced this yesterday. So this is for the 3 TeV machine and for the 10 TeV machine. Of course, the muon beam energy is then half, so it's 1.5 TeV for the 3 TeV machine and 5 TeV for the 10 TeV machine. We always have only one bunch in the machine. But then we have a very high bunching density. So we have a bunching density of around 2 times 10 to the 12. So just for comparison, this is 10 times larger than the bunching density of a proton beam in a proton bunch in the LHC. So for the presently, the proton bunch in the LHC has a bunching density of around 1.6 times 10 to the 11. So you can see this is quite a push bunching density. Of course, in the LHC, we have more than 2,000 bunches circulating in the ring, but still in terms of bunching density, it is really a high bunching density. The normalized transfer emittance is 25 micrometers, which is in fact is a large emittance because again, comparing to the LHC, the present emittance is of the order of 2 micrometers, so a 10 times smaller emittance. So it's just to give a bit of comparison with the present highest energy collider running, to say that the parameters are pushed in one or the other direction. Now, despite the Lorentz boost, these muons decay really rapidly in the storage ring. So the mean muon lifetime at 3 TeV is around 30 milliseconds in the lab frame, while this is around 100 milliseconds for the 10 TeV collider in the lab frame. So you can see here now that the exponential decay of the beam intensity. So this goes, as you see, quite fast. So we reach very low intensities very quickly. So we have to inject new bunches very frequently. And this is done here with a 5 Hertz injection frequency. So this means every 200 milliseconds, a new bunch is injected. Then also to mention here, once more, the circumference of the 3 TeV collider would be 4.5 kilometers, and the 10 TeV collider would be 10 kilometers. And this then gives a revolution time, of 50 microseconds or 30 microseconds. So just if to compare this with the muon lifetime, of course, the revolution frequency is still much larger. Okay, I don't want to say too much about luminosity because I think Daniel has a full lecture on luminosity. So I just want to say mention a few key points here. So the luminosity is, of course, inverse proportional to the bunch spot size in the interaction point. So we assume also we have Gaussian beams, sigma is the standard deviation. And you can see here that this is in the horizontal plane, this is in the vertical plane. So the star indicates that this is the value in the interaction point. And then you can calculate the spot size from the beta function interaction point, so beta star, times the normalized transverse emittance, and then also take into account Lorentz factor. So the beta star is actually quite a small value, so of the order of a few millimeters, so 1.5 millimeters for the 10 dB collider, so really a small value. And then, of course, as we said, normalized transverse normalized emittance is 25 micrometers. And then the Lorentz factor, for example, for 5 dB beams around of the order 47,000. The second point I wanted to mention here is that the bunching densities, the luminosity depends on the product of the bunching densities. So it means also that the lumi decays actually much faster than the bunching densities themselves. Yeah, so I don't want to say more about luminosity here. So here you can see once more the 10 dB collider layout. So as I said before, the collider ring has a length of 10 kilometers. It has a racetrack shape, as you can see here. It has, there are two interaction regions opposite from each other. So the interaction region is our region of interest. Then we still have 4 local chromatic correction sections, which are placed symmetrically around the interaction point. 4 matching sections to match the chromatic correction section to the arcs. And then we have 2 arc regions, so 2 arcs opposite from each other. Of course, as I said, the interaction region is really the part of the machine I'm talking about in this lecture. And also would like to highlight here that all the magnets are single aperture magnets. So this means they have one vacuum chamber. The 2 beams are circulating in the same vacuum chamber in opposite directions. And this is possible because the beams have different charges. So muon plus, minus, minus. In a machine like the LHC, where the beams have the same charge, you need separate vacuum chambers with different magnetic fields to guide the beam around the ring. Here in red, you can see once more the footprint of the 10 dB, 10 kilometer collider. This is for the example of a certain sighting study. There's also a sighting study for Fermilab. And just to say here that this is the LHC ring, circumference of 27 kilometers, which would house a rapid cycling synchrotron. Okay, so I will illustrate now in the next few slides the interaction region design challenges at the example of the present 10 dB collider lattice. Just as a disclaimer, the lattice is constantly evolving. For those who are involved in the studies know this. But still, it's just to illustrate the challenges because there are really quite a few points you have to consider when designing an interaction region lattice for a muon collider. So what you can see is now the final focus system. So the final focus system is really a very important part of the interaction region. So I'm comparing here the muon collider against high luminosity LHC. High luminosity LHC, of course, we have proton-proton collisions with 14 TeV. And as I said, of course, in the muon collider here, muon collisions at 10 TeV. So the beams are colliding here in the interaction point. And then we need these strong final focus quadrupoles, which need to be symmetrically placed around the interaction point to squeeze the beam in the interaction point. And this is realized with a final focus triplet configuration, which is focusing focusing in the horizontal plane. So as you heard yesterday in the lecture of Chris, quadrupoles, then I have the opposite effect in the other plane. So it's then a DFD configuration in the vertical plane. But you can achieve an overall focusing effect in the interaction point. So you have a small beam size in the 2 planes in the interaction point. Also in the LHC, we're using actually in a final focus triplet configuration. Just to say, there are also other configurations which exist, doublets, quadruplets. For lower energy muon colliders developed, for example, by MAPT, we're using quadruplets. And even also then other configurations, triplets combined with dipoles and so on. Because it's also important to have a dipolar component in the final focus region of a muon collider, simply because this is needed for background reduction. In a sense, you have muon decays also further upstream. The decay products would leak towards the interaction region here. And then with such a dipole chicane, you can sweep away the products. So it's important to have some kind of dipole component here. In previous lattice versions from MAP, they were using different strategies with combined function, quadrupoles and dipoles. But here we're using a dipole chicane at the entrance of the final focus region for the incoming beam. Now, there are quite a few important differences between the muon collider and halloumi LHC. And the first one, as you notice here, we have a much smaller L star. So L star is the distance between the interaction point and the first magnet. And this is about 6 meters here for the muon collider, while this is 23 meters for halluminosity LHC. So this is needed because we need a much stronger squeeze in the muon collider. So as I said in the beginning, to be more efficient for the magnets, they need to be closer to the IB. And since we have much more demanding requirements in the muon collider in terms of squeezing the beams, we have much less space. So this also means we have less space for the detector and also less space for our machine detector interface. So just to show you a bit in comparison with halluminosity LHC, because it's an existing machine, so maybe some of you know the machine. I think it's nice to get a bit of feeling how we relate to this. And then we also need high field, large aperture quadrupoles, of course, in the muon collider. So let's have a quick look at the optics functions to connect a bit to the lecture from Chris yesterday. So here you can see now the beta functions in the horizontal and vertical plane in red and in blue here along the machine. So this is the S coordinate, which is the distance from the interaction point. So up to a bit more than 150 meters. And then green, you can see the dispersion function also as a function of the distance here. So as we already heard yesterday, that the beta function describes the betatron motion of particles in the machine. And the beta function describes the modulation of the transverse beam envelopes. It's not the individual particle in this case. So it describes the modulation of the transverse beam envelope as a function, also under the influence of all the focusing and defocusing elements of the lattice. This means larger beta function with a larger beam size, smaller beta function with a smaller beam size. But then there can also be a contribution from the dispersion to the beam size because, as we also heard yesterday, dispersive particles, so particles which are off momentum compared to the nominal beam energy, they have different trajectories, and this can also grow the beam size. And this is also has to be taken into account. Now, there's one point I want to mention here. In this first part here, in the first drift space between the interaction point and the first magnet, so up to L star equals 6 meters, the beta function will increase really rapidly according to this formula. So beta star plus the distance squared divided by beta star. And beta star is, of course, the beta function in the interaction point. Beta function for 10 dB collider was 1.5 millimeters. So if you do the math here, you can see that at the final first focus magnet, the beta function, as at 6 meters, is already 24 kilometers. I know a beta function value is a bit abstract, but you will understand in a second how this relates to the real beam size. If you compare this to a luminosity LHC, the beta star is 15 centimeters, so quite a bit larger. L star is 30 meters, but then you can see that at 30 meters, the beta function is only 3.5 kilometers, still much smaller than in the muon collider. But then inside the final focus quadrupoles, the beta function grows, of course, even still much more. So we reach beta functions of the order of hundreds of kilometers. So if they're even more than 800 kilometers here in the final focus quadrupoles for the muon collider. For comparison, high luminosity LHC triplet, the maximum beta function is 21 kilometers. So it's even less than the beta function we reach already at the beginning of the first magnet. So just to show a bit the comparison here. Now, based on these optics functions, we can calculate the transverse beam size along the machine. So we assume that the beams are Gaussian. Sigma is, of course, standard deviation. And you can see here that, that you already heard this formula, so that the sigma here is given here by the square root of the beta function as a function of S times the normalized transverse emittance, of course, the relativistic factors, and also the dispersion contribution. The dispersion function now in the interaction region is by design quite small, so we can neglect this term here now for this small exercise of looking at beam sizes. So if you do the math, you can see at the interaction point we have a beam spot size of 0.9 micrometers. But then already the Q1 magnet, so after let's say 6 to 10 meters, this grows to 5 to 7 millimeters. And then in the Q2, Q3 to 10 to 20 kilometers. So we have a beam spot which is this large, already after a few tens of meters. Again, if you compare to Halloumi, the spot size, so sigma in the interaction point is 7 micrometers, while then the maximum spot size in the final focus is actually 2.7 millimeters. So we have a much smaller beam size there in this hard-on machine. Okay, now, so this very large beam size and also the need for some radiation shielding because of muon decay translates now a very significant, translates a very significant aperture requirements for the magnets. So what is the aperture? So the aperture is essentially the inner pore diameter, or in other words, it's the inner diameter of the magnet coil. So this is a very important parameter for designing magnets because it becomes more challenging the larger the pore diameter. Now, if in order to determine the pore radius, pore diameter we need, we first need to define the required beam clearance, so our vacuum aperture. This now for the muon collider, we assume that 5 sigma. Vacuum aperture is sufficient, so 5 sigma, as you can see here, until the vacuum boundary is sufficient for muon collider because the beams are only stored for a few thousand derms. In other machines, again, taking Halloumi, I know it's a proton machine, but we store the beams for hours, even more than a day, and there you have a much more processes which leads to tail population. So we need, for example, a much larger aperture. But then we also need some additional space for shielding and other equipment like vacuum chambers, supports, insulation, and so on. This adds another 8 to 10, 11 centimeters to the pore diameter. So we end up in the end with really large pore diameter. Let me still show the following. You have here in this plot as a blue and red curve the 5 sigma beam envelopes. You can see here this reaches 10 centimeters already here. So this means that we need a really large vacuum aperture. But then what you can see here, these boxes are in fact representing the pore radius, the magnet pore radius for the different magnets. You can see in the Q1 where the beam size is still a bit smaller, the pore radius of the order of 7 to 10 centimeters. But then in the other magnets here, we have a pore radius of 15 centimeters. So just to say, the pore diameters of the order of 30 centimeters, you have to imagine this is that big. And this is twice as much for the high luminosity LHC final focus quadrupoles. Large physical aperture means also that more particles can leak towards the interaction point, so more decay products, and this increases also the beam-induced background. So the design of the interaction region is very much also linked to the MDI design. Very briefly, one last slide on the interaction region. So a larger pore diameter, as I said, also reduces the achievable focusing strength of a magnet, of a quadrupole, for technical reasons. And Luca will talk much more in detail about this late in the lecture. I think it's maybe later today or tomorrow. So just to give you a bit of an impression, so this is a magnet for the high luminosity LHC. This is a magnet which is presently built partially in the US, partially at CERN. It has a magnet pore aperture of 15 centimeters, and there's a gradient of 130 Tesla per meter, and this is based on niobium 13 superconductors. If you look now at this graph here, which shows the pore diameter as a function of the gradient, then this black curve here gives now the maximum limit what can be achieved for high temperature superconducting magnets, so for REPCO-based magnets, operated at 4.5 Kelvin. So this limit comes from technical considerations in terms of the stresses, but it also includes, for example, some cost considerations. Luca will talk much more in detail about this. Just to say that now for the example, for the Q1 magnet, where we still have a small aperture, as I just said before, we would need of the order of 200, 300 Tesla per meter, while for the Q2, Q3 magnet, where we have actually a larger bore diameter, we can only have smaller gradients. So you can see of the order of 100, 150 Tesla per meter. So in fact, a similar gradient as for Halloumi. Sorry, but just with a large aperture. There are other challenges. We're very sensitive to magnetic field errors. We're very sensitive to misalignments, to magnet vibrations, and so on. So it's just to say that the action region design is quite involved. So a few takeaway messages just for the interaction region. Tight space constraints for shielding and detector because of magnets need to be close to the IP. Large physical vacuum aperture, secondary radiation can leak to the IP and increase the background. Very challenging requirements for the magnets. So let's come now to the beam-induced background and all the radiation issues. So the second part of this lecture. So the collider is a very hostile radiation environment. As you see later, we get a mixed field of different particles, leptons, photons, and hadrons. There are three essentially main issues we have to deal with. The first one is the heat load in the superconducting magnets. It's very inefficient to extract heat from the superconducting magnets. There are also technical limitations how much heat you can extract, and it's very costly. So if you need a cryogenic plant, this could cost a fortune. So we need some shielding on the inside of the magnet, which is not at cryo temperatures, which extracts the heat. The second important point is, of course, and this is the main focus in the rest of the lecture, the beam-induced background is also an instantaneous effect because it can perturb the physics reach. And the third point is more about cumulative effects, about radiation-induced aging of machine and detector components. So how is our design approach for the muon collider? Of course, we don't have any test setup to play with. We need to do this via simulations. So first of all, we have to understand and model all the different radiation sources. We have to simulate the radiation transport and secondary particle production in the machine and in the detector. For this, we use Monte Carlo simulations. There are already very sophisticated tools available like GN4, Fluker, Mars, and other codes. And then we have to quantify the effects in the machine. So this is, for example, one muon decay showing all the secondary particle tracks. So you have secondary neutrons, photons, charged hadrons, electrons, positrons. There's even some particle cut because if I would show the particles down to low energies, you would not see much anymore except the particles. So it's just a high energy particle shown here. And then we have to develop mitigation measures like shielding. So what are now the different sources of beam-induced background? We have single beam sources. So these are sources which do not depend on the presence of the other beam, and I would call them diluted sources because they occur essentially all around the ring. Muon decay, I don't have to say much, you know everything about it. So this is the dominant source, clearly the dominant source. And if I say afterwards other sources are minor, it's always in comparison to muon decay. Synchrotron radiation emission by the muons themselves, as it was already mentioned yesterday briefly also, if a charged particle is spent in a magnetic field, it emits photons. These are synchrotron photons, but this depends, the energy emitted depends very strongly on the mass of the particles and the fourth power inverse. So you will see, if you do the math, that electrons, you get a lot of synchrotron radiation, muons, you get much less synchrotron radiation. This is a minor source, so the synchrotron photons emitted by the muons is a minor source. Beam gas scattering. In a vacuum chamber, you have never perfect vacuum. You always have some residual gas. And the muon beams can now interact with this gas. It can be subject to Coulomb scattering. It can emit Bremsstrahlung photon, and they, of course, can also emit electron-positron pairs. Now, these emitted electrons, positons, and gammas are not expected to a major source. also the muons, they receive a kick because of the energy loss. They could also be lost in the machines themselves. But also this is expected not to be a major source, but needs a bit more studies. Then there can be beam losses driven by beam dynamics, and maybe Elias will talk a bit more about beam dynamics, also collective effects, for example. So here, when I say the beam dynamics, this could be many different effects, instabilities, resonances, and so on, what we heard about already yesterday. So we could lose the muon on the aperture, and this can also produce a background. We cannot exclude at this stage, this is also major, not a major, but a significant background, but we don't have yet quantitative estimates. And then there are single beam sources. So these are, the two beam sources. These are now sources which do depend on the presence of the other beam. And these are radiation sources which are confined in the interaction region. So first we have Beamstrahlung. So what is Beamstrahlung? When now the bunches collide, then a muon of one bunch can be bent by the collective field of the other bunch, and it can emit photons. And this is what we call Beamstrahlung. The Beamstrahlung photons themselves, I will come back to this later in the presentation here in this lecture. There are not so many Beamstrahlung photons compared to, for example, linear colliders, and this is a minor source here for the muon collider. But there are other processes which are partly related. So we have incoherent electron-positron pair production. So this is an electron-positron pair created through the collision of photons, which are co-moving with the muons of the counter-rotating bunches. And these photons can be now real or virtual photons. The real photons are actually the ones produced in Beamstrahlung. Incoherent pairs are expected to be a significant source, not as much as muon decay, but also a significant source, but only for the detector, not so much for the machine. Radiation of the machine is not so much influenced by this. Then we have coherent pair production. So this is different. So here an electron-boson pair can be created by a photon in the collective field of the counter-rotating bunch. Again, so real virtual photons, and the real photons again come from Beamstrahlung. But because we don't have much Beamstrahlung, coherent pairs are expected to be a minor source. So this is pretty much suppressed in the muon collider, at least at these energies. If you would go to 100 TeV muon collider, then it becomes more important. And then, of course, other processes, muon-muon collisions can lead to muon losses, but this is expected to a minor source. I have to say that the muon losses because of different beam-beam effects. So here we're talking about the secondary particle production, but then also muons can be lost eventually, can form a beam halo, can be lost. But we don't have yet a quantitative estimate. This depends also on the machine lattice and the dynamic aperture, and we don't have yet an estimate on this. Yeah, of course, it's a typo. Thanks. Red and blue is always different charges. Sorry. Just a few key messages for the radiation sources. So muon decay is clearly the dominant source for both the machine and the detector. Incoherent pair production is a non-negligible source for the detector. Beam halo losses could be a potentially important source. This is essentially halo loss means that many particles, many processes can form a halo, beam effects, but also even beam gas scattering, maybe not to a big amount. And if these particles will be lost or not depends on various factors, for example, on the dynamic aperture of the machine. So there's a beam dynamics concept that particles become unstable and then they're lost. What helps is that the muon beams are only stored for a few thousand terms. It's not like the LHC, the beams are stored there for hours. Here it's only for a few thousand terms. So the halo formation is not that pronounced, but is not yet studied in that much detail. Okay, so for the moment, we don't have a quantitative estimate how much this matters. I really have to speed up a bit, but this is an important slide, so still stay maybe a bit on this. So how can we cope with radiation, and how in particular can we reduce the physics background? First, I think everybody in this room has already heard about these nozzles. So these are these forward conical shielding elements, and they shield the detector from high energy decay products, but also from secondary showers produced by beam halo losses. Then we need these conical liners on the inside of the magnets. They follow the 5 sigma beam envelope, and they protect the magnets. In a sense, these liners are not at cryogenic temperature and room temperature, so here they extract the heat from the mu and decay products. But they also prevent that some of the decay products leak to the interaction point. So this is also part of the background mitigation measure. Then what also helps is the interaction region lattice design. So a customized design can also reduce the loss of decay products in the IP. So decay happens somewhere. The decay positons, electrons can reach some other position before the impact on the aperture. We want that they are not too close to the interaction point, but further away. And this we can partially influence through the magnetic field configuration of the interaction region lattice. We might need a transverse halo cleaning system. This means we want to have a system which removes halo particles, but far away from the interaction point, such that they're not lost close to the interaction point. What helps is also the detector solenoid, because, as I will mention in the end, for example, the incoherent pairs, they're influenced by the trajectories, they're influenced by the detector solenoid. And this can help to prevent that they reach the inner trackers, for example. And all the background which we cannot handle with all these measures, so which is then remaining, needs to be handled by the detector, so suitable choice of detector technologies and reconstruction techniques. Now, very briefly, the nozzle. This is a legacy of Fermilab, Nikolai Mokov and colleagues. So developed this nozzle design for the 1.5 TeV collider. And it turned out that this nozzle works very well also for the 10 TeV collider without much modification. So the nozzle is essentially almost 6 meters long, so about the length of L star. It had the nozzle base is 1.2 meters, so here just show half of it. It is made of tungsten as a shield for electromagnetic showers. And on the outside, it has ported polyethylene to moderate and capture neutrons. So this is the main principle and geometrical, this is the geometrical features of this nozzle. And we're using just a very similar nozzle, but small modifications also for the 10 TeV collider. Now, muon decay is a radiation source. Everybody of you is familiar with muon decay. I just still want to recap once more. We get 2 neutrinos. For the radiation load to the machine, and in terms of physics background, we don't care about the neutrinos. We care about the electrons and positrons. And I just wanted to show here the spectra of the electrons in the collider ring. You can see it for 3 TeV machine, the 10 TeV machine. So we have a continuous spectrum up to the top energy here. And the average energy carried by these electrons and positrons is about 1/3, a bit more than 1/3 of the muon energy. So it's about 500 GeV for the 3 TeV machine and 1.5 TeV for the 10 TeV machine. Now, we know how muon decay happens. How does this now lead to background? So this is a squeezed view of our interaction region. We have here the final focus magnets. Just to say that this is a length here of around 60 meters, and this is only 60 centimeters, so really a squeezed view. The final focus magnets, as I said, the internal radiation shielding, these are the magnet coils in orange. These are our nozzles, this is our detector, which is not shown here. And now, this is of course the vacuum, and now we have here an incoming muon. I don't show the full muon beam, just one muon. 5 muon plus, 5 TeV energy. And it decays in this position here. It creates now a positron, in this case of 1.2 TeV. And now, because of the lower magnetic rigidity, this is strongly overbent by the magnetic fields. And then there's another important point, because they have a much lower mass, the positrons. They emit a lot of synchrotron photons in the magnetic fields. So the yellow lines here, these are the synchrotron photons emitted by this decay positron. And you can see when the positron impacts here on the aperture, it has an energy of 450 GeV. So it lost 750 GeV in the form of synchrotron photons. So it means that it's not only decay products which impact on the aperture, it's really also a lot of synchrotron photons. Now, what I'm showing here in this next plot is not from a single event, but this is now the spectrum of the letter G spectrum of photons and positrons impacting in the final focus on the inside of the final focus magnets and on the inside of the nozzle. So essentially, they are impacting on the vacuum aperture in the first 46 meters. And you can see that we have a wide spectrum. So the synchrotron photons even can reach TeV energy. So it's only very energetic photons. And then you can see also that the positrons still have a wide spectrum, also up going to very high energies. Now it's very important to understand how these particles interact with matter. So how can we shield these particles to reduce the beam-induced background? And this also partially relates to the interaction of particles with matter, as Kevin already introduced before. So I'm trying to pick up on a few points, but maybe I have not so much details anyway in this. So in this sense, electromagnetic showers, you heard this before, just very briefly without going too much into details. First of all, I want to stress that the decay electrons, positrons, but also the photons, they give rise to electromagnetic showers in a similar way. So in the end, it doesn't matter if you start with a positron and photons, there's a small difference in the shower length, but this is negligible. So you have, of course, the high energy electrons and positons lose energy through Bremsstrahlung. As you already see also in the electronic stopping power, you have at low energies, you're dominated by ionizing energy losses, but already at above, let's say 10 MeV, you have radiative losses which dominate, so Bremsstrahlung emission. And then these Bremsstrahlung photons have high energies, they can produce electron-positron pairs. This leads to a multiplication of particles, as we heard before, and this is what we call the electromagnetic shower. Of course, the energy of the particles from shower generation decreases and decreases, and then this multiplication stops when we fall below the critical energy here, where more or less the ionizing energy loss and the radiative losses are equal. I just want to highlight here one point about the shower maximum. So the shower maximum is the position where the number of shower particles is maximum, and then it goes down again. And this is dependent on the materials, of course. So this scales now with the radiation length, as also Kevin introduced already before. So now, in order to shield these particles before reaching the detector, we want to have a material with a short radiation length, because this means that we stop the showers much earlier. So that's why the nozzle is made of tungsten. And that's why this is our preferred material. Tungsten is a very expensive material, just to say also. So if you can use lead, you pay per kilogram 1,000 less, a factor of 1,000 less, but we are very constrained in space, so we use tungsten. But then it's also important to mention that the depth of the shower maximum in a material depends on the logarithm of the initial energy. And this is very helpful because it means that the shower maximum for 1 TeV electron is not so much further than for 10 GeV electron. I will show this afterwards. So this plays in our favor. But it's not only showers, there are also other particles produced. We can produce in particular secondary hadrons and muons. So the main channel to produce muons is simply muon pair production in the Coulomb field of the nuclei. So this the main process is beta-Heitler processes. So we call them beta-Heitler muons. The cross section is of course much smaller than for electron-positron pair production. So this hadron muon production is happening with a much lower cross section. So we produce much less of them, but the muons, of course, much more penetrating. And then hadrons are produced mostly through photonuclear interactions. So you can see a generic plot of how such a photonuclear cross-section looks like as a function of the energy. We have different resonances, the so-called giant dipole resonance you might heard of about, and then other resonances like delta resonances. And then according to these resonances, then this is where most of the hadrons are produced. So typically you can see the GDR for tungsten, our material of choice for the nozzle. And you can see the giant dipole resonance is at the energy of the order of 10 to 20 MeV. So this is where we produce a lot of neutrons. Neutrons are much more difficult to shield than the showers. I don't have time to go into any details about Newton interactions. We can discuss this offline if you want. But the cross section is very complex for Newton interactions. They scatter lots because they have no charge, and that's why also the range is much further. But of course, with a lot of scattering events. So just to show you a bit, putting this together, how can we shield now our decay products, which have an energy range up to TeV, as I said. So what I'm showing here is a generic example. I'm shooting here in this case a 10 GeV electron on a tungsten block, and here 1 TeV electron on a tungsten block. And what you can see is the following. This is the particle fluences, secondary particle fluences as a function of the depth. Is transversely integrated. I don't look now at transverse shower shapes. And I assume you have perpendicular impact. So what you can see here is this is the shower buildup. So these are the photons and the electrons and positrons. And the shower maximum is already reached after 2 centimeters here. For the 1 TeV machine, already after 4 centimeters. You see, not much further. So we are also very efficient in shielding the showers. So essentially, after 10 to 20 centimeters, we have very well shielded our showers. The particles go down. But photonuclear interactions kick in already here. We produce a ton of secondary neutrons. And then afterwards, the secondary neutrons dominate. But then you still have secondary electrons and positrons, as you can see here, and photons and secondary electrons and positrons. They're not shower particles. These are particles which come then from neutron interactions, produce photons, and again, they can produce electrons and positrons. This means that all this long tail is dominated by the photon neutron production and the following processes. There would also be muons, which I did not plot here. They're maybe around down here, the beta-Heitler muons. They give yet a different problem because the range is, of course, can be hundreds of meters. They can easily reach a detector from far away. So it's just to show a bit the complications, how we can shield particles produced in muon decay. Now, just to show a bit of the anatomy of muon decay, we have here a muon coming in. Again, the squeezed view of the interaction region. The particle muon decays. It is bent a bit, emits circular photons, produces the EM showers, produces secondary neutrons through photonuclear interactions, and beta-Heitler muons in addition, which are not shown. Now, the nozzle. So the nozzle shape and the material of the nozzle is very important to determine the spectra, the entry positions, and also the directions of secondary particles which are entering the detector. We change the nozzle shape, we change the nozzle material, this will change. The nozzle reduces the background particles by orders of magnitudes. So it's not a small reduction, so really orders of magnitude. The other measures like changing the lattice, avoiding the too many decay products are lost nearby the interaction point is a secondary effect. So here we can reduce the background by a factor of a few, but not by orders of magnitude. So this is important to keep in mind. Now, this is how a typical background spectrum looks like. So it's again a lethargy spectrum. You have, for example, a lot of photons. You have a lot of neutrons. The neutrons are partially the thermal neutrons are suppressed because we moderate them and capture them with the porrited polyethylene here. And then we also have, of course, secondary hadrons. So sorry, bad statistics here, but which are also reaching up to GeV energies. So we're not talking, sorry, hadrons, I mean charged hadrons in this case, not only hadrons, and then also some muons. Here you can see some numbers, typically how many background particles we get per bunch crossing. So 10 to the 8 gammas, 10 to the 7 neutrons, and 10 to the 6 electrons and positrons. Daniele will explain this much more in detail, so I don't want to say much more about this. Just one last word about muon decay before moving on to the other sources of background. So what you can see is now the number of particles entering the detector envelope, but as a function of where the muon decay happened along the machine. This means if a muon decay happened here, it produces, so about, let's say 3 10 to the 2, these are positrons will enter our detector. So these are not the particles produced at these locations, but this is how many particles produced from a muon decay at this position enter the detector. So here the key message is the following. that it's mostly muon decays in the final focus which contribute to our background. So when the curve is higher, means more contribution. There's not a non-negligible contribution from further away, but this we partially treat through having this dipole chicane. Again, I let Daniele then express this in a much more elaborated way. Also, just to say that the beta Heitler muons, which are produced by photons in the electromagnetic showers, they can contribute even if they produce much further away, even hundreds of meters away, simply because they have a much longer range. So when we talk about background, so gammas, neutrons, electrons, positons are mostly because of muon decay in the final focus region. Muon background is mostly because of from secondary muons is mostly because from all over the let's say last hundreds of meters. I don't want to spend too much time about beam halo losses because it's a topic we have to say we are less advanced yet in our knowledge. So what are beam halo losses? Beam halo losses essentially, so let's start with what are halo particles. So halo particles are particles which have a large betatron amplitude for one or another reason. They got a kick or whatever. Or they can also be beam dynamics effect, you know, as we heard yesterday, it could be resonance, whatever. But then these are also particles which have a momentum offset. So off momentum particles, and also this can lead to a large physical oscillation of the beam particles. So as I said, many different processes can lead to a formation of a beam halo. Beam halo formation is a very complex subject. Even in the LHC, after more than 15 years of operation, we cannot say with certainty how the halo is formed. A lot of studies to understand the halo properties, but there are different mechanisms contributing. The mechanisms here will be probably different than in a harder machine like the LHC. Now, when the transverse amplitude of these particles exceeds our physical aperture, so meaning here, for example, in the action region at 5 sigma, these particles are lost, they interact with the material, and eventually can contribute to the detector background. Now, a bit of the anatomy of this background. I mean, decay electrons and positons, as you saw, we can stop in terms of showers with a few tens of centimeters. Here, the muons, they can easily penetrate tens, hundreds of meters, depending on the energy. So this means even if a muon is lost further upstream, it can reach the detector. But there's another point. On the way, they produce electromagnetic showers because also, as Kevin said before, they're subject to radiative losses. I will show this also on the next slide. So this is direct electron-positron pair production, which is dominating at these energies at 5 TeV. They can also emit Bremsstrahlung photons, and there can also be photonuclear interactions, a bit with a smaller cross section. And again, depending where this happens, this can happen deep in the nozzle, and then we get a shower in the detector. So it really depends where this happens, but of course the likelihood this happens is still smaller than, for example, for an electron or a positron. So let's have a closer look at the energy loss of a high energy muon. So again, this is what Kevin already showed. So we have a 5 TeV muon. We're in a regime where radiative processes are dominant. But here you have a decomposition of the different contribution. You can see that this is the total stopping power. But this curve here is direct electron-positron pair production in the Coulomb field. And then here you have Bremsstrahlung emission just a bit below. And then these are the photonuclear processes, and this is ionization. So you will mostly have Bremsstrahlung and direct pair production. And just to say that also the energy which can be transferred to the Bremsstrahlung photons or to the electron-positron pair produced is not the same because there are different contributions here. For example, a large energy transfer to a secondary particle is rather likely because of Bremsstrahlung. And then here you can even lose a significant fraction of the muon energy and you produce an energetic shower. So just to show you one picture simulated by Daniele. So this is one muon halo loss on the aperture. And you can see on the way it produces a lot of showers. secondary photons, secondary electrons and positrons. And then again, you have secondary showers, which produce neutrons and photonuclear interactions and so on. So it's quite a complex picture in this sense in the radiation fields. Not going in details here, again, referring to the lecture of Daniele this afternoon, you get white particle spectra as a decay-induced, as a halo-induced background. Okay, just to say, the mitigation measure for halo-induced background is that we reduce the beam tails, remove this part of the tails far away from the interaction point. In any other high-energy collider, we have collimation systems far away from the interaction point, which clean the beam halo. And this is usually done with classical collimation systems, so material blocks, they're brought close to the beam, and then these particles are removed from the beam in a controlled way. You need secondary absorbers and so on. Doesn't work well with TV muons. Studies done by Fermilab, they showed the muons, they don't interact much. They get a bit of disturbance. They lost in the aperture bottleneck, which is our interaction region. So we have to come up with some alternative concepts. So again, at Fermilab, already in the 1990s, there are these ideas of extracting the beam halo with Lambert's and Scepter. It's maybe something to be demonstrated how this works. They even now other proposals. There was a paper actually this year to do halo cleaning with crystals, where of course you have a good efficiency for negative muons and a very bad efficiency for positive muons. Sorry, for a good efficiency for positive and very bad for negative. So it's also maybe not the final word. This is something to be studied, but first of all, we have to understand halo formation for muon beams, which are stored for only a few thousand turns. And this is something, if somebody wants to do a PhD about this, I think there are a lot of opportunities. Last point, incoherent electron boson pair production as a radiation source. So some of you have already heard about this, maybe because if you do in detector simulations, you might have already taken these distributions. So as I said, these pairs created through the collisions of photons moving with the muons in this sense, in a simplified picture. You distinguish now three processes. So I stole this plot from the PhD thesis of Daniel, which was not on muon colliders, but was on linear colliders. But essentially also here we have essentially three processes depending if the photon is a real or virtual photon. So Breit-Wheeler, Bethe-Heiter, Landau-Lifshitz, and the real photons that come from Beamstrahlung. I'm putting here also two references from the 1990s. I think these are quite good references describing pair production, incoherent pair production, but also coherent pair production in muon colliders on beam effects in general. So there's not so much more literature about this. So I just want to mention one point, since, as I said, Beamstrahlung is a source of real photons. But in fact, for the muon collider, so let me first one step back. Beamstrahlung again. So Beamstrahlung means that a high energy charged, charged particle can be deflected by the high charged particle density of the other beam, so by the collective field of the other bunch. And then when it's deflected, it emits a photon, and this is what we call the Beamstrahlung. Now there's this Beamstrahlung parameter epsilon. I have some formulas how you do calculate it in the backup of this presentation. So the slides, I think they will be distributed. And you can see the epsilon parameter. The smaller it is, the less severe is essentially Beamstrahlung in this sense, in a simplified way. You can see here for the muon collider 10 TeV, this is quite small. This is for FCCE, and then this becomes larger for linear colliders. Sorry, I forgot to include now this number here. But we get essentially, on average, 0.2 photons per muon during a bunch crossing. And the average energy of this muon is 1.6 MeV. And then you see this can reach very high values for linear colliders. So now, since the Beamstrahlung emission is small compared to other colliders, that's why incoherent pair production in the muon collider is more dominated by the Landau-Lifshitz process. while, for example, in click and RLC, and then also in the cool copper collider, which was another proposal, I think that there was a more balanced contribution. It was most, Peter Heitler was a bit more dominant, and then there was still Landau, Lifshitz, and then also Breit-Wheeler, because these are real photon conditions was less. Again, you can find here some references. So this is the energy spectrum calculated with Guinea pig. As a code which can simulate this, but again, Daniele will show some more details. So how can we now deal with these incoherent pairs? There's another effect which you have to take into account. So once the electrons and positons are produced, they can still get a kick by the collective field of the bunch. So you produce a positron, and then if you're in the Riemann bunch, it can get kicked away. And this means it can get a large transverse momentum in the sense, and then it can -1 minute. Yes, I'm almost done. Huh? This is my last slide, almost. So they can get a large kick, and then they can enter the inner tracker. So this is a problem. In addition, the trajectory of this particle is also affected by the field of the detector solenoid. So the stronger the detector solenoid field, to some extent, can help to reduce the pairs which enter now in the detector. So just to show here a few lines, again, this is a plot produced already in the 1990s. I think this was from somebody from Fermilab. And you can see a different trajectories of the incoherent pair electron or positron. I don't remember now which one this was. And then you can see some of them, they're confined in the nozzle, but then the one with the large transfer momentum can get in here into the detector. Okay. The workflow, which Daniele will show in the afternoon, no more comments here. And just to say, as really my last slide, we have a conceptual idea of how an MDI should look like for muon colliders. We're still quite a bit, we still quite need a bit of work to work towards a realistic MDI design. A realistic MDI design means that we have a technical design, a full integration, take into account all the space needed for services, cryogenic distribution lines, supports, and so on. We need also an engineering design, for example, for our nozzle. How do we manufacture it, assemble it? How can we maintain it? How can we extract the heat? How can we deal with alignment, vibrations, tolerances? How can, in the confined space of the detector, this be supported? So a lot of engineering work ahead. Other points which I did not address here because they're also not very much advanced yet, luminosity measurement, forward detectors. So these are all problems which are not showstoppers. I think they're interesting for if somebody wants to join for such kind of work. I think we would be highly appreciating this. And that's when I'm finished. Yes, thank you very much. So I managed to squeeze a 1-hour lecture in 45 minutes. I'm sorry for speaking a bit fast.
Any quick, urgent, burning question over there? One moment, we need the mic.
You made a lot of statements about the aperture of the magnet, but then you concluded and said that the aperture of the magnet, the larger aperture magnet, increases the detector backgrounds. Can you explain that in a little, like over the...
Sorry, can you speak?
The large microphone. Oh, I don't. Okay, the larger aperture magnets induce more beam-induced background. Can you just go over that one more time?
Yes, we can go back to this. Maybe I can show them this plot here. So it's a there are two effects which come together here. So a large aperture means that particles which are of rigidity, like the electrons or positrons, they can have a longer range until they impact on the aperture. So if the aperture would be more constrained here, they would be lost earlier. And this means the closer we are losing them at the detector, the closer we induce showers here, the more likely they're leading to background. but it's also depending on the gradients here. For example, here we have larger aperture, we have lower gradients. So it means the overbending is not as strong. It means, again, this increases the range of the particles to some extent. So what we would prefer, I mean, if you don't care about all the other constraints, small aperture, high field, because this clears out much faster the decay background. And decays which happening further away, the particles, second particles are lost much earlier. And then we have much more shielding material until the detector. So this is what I meant with that. You can also ask questions afterwards, or maybe in the discussion session.
Yeah, exactly. We will have 1 hour discussion after
Exactly.
in the afternoon. So I would say now we are a bit behind schedule, so we take a 10-minute break. So everybody be back at 11:30.